Hello students, let's learn flow through a circular tube. Flow through a circular tube. In many chemical engineering processes, one come across a fluid flowing in a circular tube. It's a fundamental concept in fluid mechanics. Flow through a water flowing through a circular pipe, pipe flow. The flow of fluid through a circular tube can be either laminar or turbulent. So laminar flow are characterized by smooth and orderly flow, while turbulent flow are chaotic and irregular flow patterns are seen. Velocity distribution across a section, ratio of maximum velocity to average velocity, shear stress distribution, drop of pressure for given length are some of the parameters that can be determined for the pipe flow. So this we are going to discuss. Hagen-Poiseuille's equation for fully developed flow. So let's consider a cylindrical pipe. A cylindrical pipe with length L and width twice R. That is radius from center of the pipe to the wall of the pipe is R. Now fluid is flowing like this. Here. So force acting on fluid is due to gravity. This fluid is laminar and in Z direction only. This is Z direction. This is R direction and this is theta direction. Rotation of the uh, fluid will be at theta direction, but this fluid is only moving in Z direction due to gravity. It's falling from the tube. So force acting on it is first acceleration due to gravity, mass into acceleration. So mass is density into volume into G. The volume of the circular pipe, cylindrical pipe is 2 pi Rn into rho G. So this is my force acting on fluid. This force is laminar because no flow in other direction, unidirectional flow. So Vz, but V theta and Vr is equals to 0. Flow Vz because of Z direction flow. Also laminar flow, Reynolds number 1800, and fully developed flow. So how a fully developed flow look like? This is my pipe. Fluid is flowing like this, forming this kind of velocity distribution. This is my Vz maximum. Here velocity is maximum, while at the corners velocity is equals to 0. So this is my fully developed flow, that at center R velocity is maximum, but at center R equals to 0. At center R equals to 0, velocity is maximum. At R equals to R, velocity is minimum. So this is my fully developed flow that I am going to see. Other than that, it's a steady state flow. The flow is steady. No other, nothing is changing here. So molecular distribution in the flow here at the center, it will be like this at some distance. So it will be moving faster, and shear stress acting on it will be less. While at the boundary, shear stress is maximum. Therefore, velocity distribution here is less because of near molecules causing friction in the with the boundary layer, with this wall, and will not be moving faster. So velocity here is almost 0, but shear stress is maximum. Shear stress is maximum at boundary, but here shear stress is at some finite, and velocity here is maximum. Now to find momentum flux, in z direction. Why in z direction? Because the fluid is flowing in z direction only. Cut this pipe into vertical half. We get a this is like this, of length L and radius R, axial view of the pipe when cut vertically. So what's inside? Consider a shell inside it. This is my shell. This is a small shell of thickness delta r, at distance small r. So this surface becomes r plus delta r. This surface r plus delta r. So this is my shell, a small shell of thickness delta r. This is the tube wall. Now fluid is flowing in z direction. So Vz is my velocity. No flow in r or theta direction. So Vr and Vz is equals to 0. Now shear stress acting on shell here at z equals to 0 and at z equals to L is tau Rz at the surface shear stress acting on shell is tau Rz at surface R and negative tau Rz at surface R plus delta R. So this becomes a momentum flux equals to 2 pi RL tau Rz at R surface minus tau Rz at R plus delta R. Why shear stress on Z direction is not considered? Because momentum flux in Z direction, that is tau Z at Z equals to 0, and tau Z at Z equals to L they are neglecting each other because of no end effect. Whatever fluid is flowing through pipe is coming out. So whatever bulk is going here at this is coming out. Therefore, because of no end effect, these are cancelling each other, and therefore momentum flux in z direction is this. This is a incompressible fluid, so no effect on viscosity. And density. Therefore, density and viscosity is considered constant. So these are the assumptions that we took for axial flow in circular tube. Steady state condition, laminar flow, Reynolds number 1800. Incompressible fluid, density rho and viscosity mu is constant. Unidirectional flow, Liquid flow is only in z direction. V theta and Vr is equals to 0. Newtonian fluid, no slip between liquid and solid surface of the wall, no end effects, disturbance of flow of liquid at edges, z equals to 0 and z equals to L are neglected. The flow of liquid is under gravity only. Now applying a momentum balance at shell. Rate of molecular momentum in minus rate of molecular momentum out across the surface at r and r plus delta r plus acceleration due to gravity. So what it is, 2 pi rl into tau rz at r minus 2 pi rl at tau rz at r plus delta r. R is the surface and z is the direction, plus rho g into 2 pi r L into delta r. Why? Shell. We are applying it on shell, therefore delta r. Now dividing by 2 pi r, 2 pi delta r L. Don't divide it by r is the variable. Divided by delta r and taking limit that is r tends to 0. Delta r tends to 0. Tau rz r into tau rz at r minus r into tau rz at r plus delta r upon delta r limit r tends to 0 plus rho g r equals to 0. Now this equation becomes d by dr r into tau rz equals to rho gr. Now on integration, what we get? R tau rz equals to rho g r dr. This gives me equation r tau rz equals to rho g r square upon 2 plus c1. Now tau rz equals to rho g r upon 2 plus c1 upon r. Now to find value of c1, I need to find value of c1. So I'll put boundary conditions. Putting boundary conditions at r equals to 0 and r equals to, boundary conditions are at r equals to 0 and r equals to capital R, right? This is my radius of pipe, so at capital R, but I am putting boundary condition for r equals to 0 to find c1. Tau rz, what will be tau rz at this condition? It will be finite. Why it will be finite? Molecular, there must be some molecular distribution and hence linear momentum flux distribution. So linear momentum flux distribution is finite, which will be increasing at boundaries. So at r equals to 0 it will be maximum, but at r equals to at r equals to capital R it will be maximum, but at r equals to 0 it will be some value. So putting this value, I get C1 equals to 0. So putting this value C1 equals to 0 in the equation 1, I get tau Rz equals to rho gr upon 2. Now using this equation in next slide. So tau Rz equals to rho gr upon 2 was the last equation, equation 2. So by Newton's law of viscosity, what I get, minus mu dvz upon dr equals to tau Rz. Putting this value in equation 2, I get dv equals to dvz upon dr equals to rho gr upon twice mu in negative direction, minus sign, with minus sign. Now integrating this value on integration, what I get, minus rho g upon twice r integration of r dr. This becomes Vz is rho g upon twice mu into r square upon 2 plus C2. Now to find value of C2, which is equals to minus, I have to put boundary conditions. For velocity profile. So velocity is, if you see velocity going on this circular pipe, velocity at r equals to 0 is maximum, right? While velocity at r equals to capital R is equals to 0. So to find value of C2, if I put at r equals to capital R, boundary condition, at boundary condition r equals to capital R, Vz equals to 0. Therefore 0 equals to minus rho g r square upon 4 mu plus C2. This r square is capital R. So substituting, so what I get? So C2 is equals to rho g r square upon 4 mu. Substituting value of C2 in equation 3, I get Vz equals to minus rho g r square upon 4 mu plus rho g capital R square upon 4 mu, which gives me r square minus r square rho g into 4 mu, right? This is my Vz. Now taking r square out, I get 1 minus r square upon capital R square. So see, this equation is also parabolic. Therefore, velocity profile is showing me a parabolic equation, and thus it's parabolic in nature. Right? Velocity distribution is parabolic. Now if I want to find maximum velocity for this, what I get? So to find maximum velocity, Vmax is equals to, I have to put r is equals to 0, small r is equals to 0. So what I get? Rho g r square upon 4 mu for maximum velocity. Now to find average velocity is equals to volumetric flow rate upon area. So Vz average is equals to, from 0 to 2 pi, from 0 to r, Vz r dr d theta, because r and theta direction, upon area. What's the area? R dr into d theta. So d theta is 2 pi. So 2 pi get cancelled. So previous equation was Vz average is equals to 0 to r Vr r dz dr upon r dr, which becomes r square upon 2 Vz r dr. Which is equals to rho g capital R square upon R 1 minus small r square upon capital R into small r dr, integration 0 to r upon r square by 2, which is equals to rho g this gets cancelled out upon twice mu into r minus capital small r cube upon capital R square into dr by multiplying by r. Now rho g upon twice mu, putting integration 0 to r, r square upon 2 minus r to the power 4 upon 4 r square. R square get cancelled. What we get here? Rho g r square upon 8 mu, right? So Vz average is equals to rho g r square upon 8 mu. Now to find mass flow rate, what is mass flow rate? Its velocity into area into density. So velocity is rho g r square upon 8 mu for average velocity into rho into area, that is pi r square. This we get rho square g r square into r square upon 8 mu. That gives me rho square g r to the power 4 into pi upon 8 mu. While force exerted at wall we get small r equals to capital R. That is in place of small r we have to put so what will be force exerted? Two pi rn into minus mu dvz upon dr, that is small r equals to capital R, or we can write pi r square L into rho g. Thank you.